Hi, today we are going to find the electric potential due to an electric dipole, and then from the equation of the potential, we are going to derive the equation for the electric field. As shown in this figure, we see an electric dipole which is consistent of two opposite charges represented by plus Q and minus Q. And these two equations are separated by D, which is the modulus of some vector D, which starts at minus Q and ends at plus Q. Also, this D vector is centered by the origin. We assume the origin to be at the center of this vector, and accordingly, this vector is divided into two subvectors, same in magnitude, which are plus D over 2, which is this vector, and minus D over 2, which is the lower vector. Now, the potential of P, the potential at an arbitrary point in the space P, can be easily found from this equation. V is equal to Q over 4 pi epsilon R, where in place of Q we put the charge, and in place of R we put the distance between the charge and the point where we want to measure the electric potential at. Now, let's set further parameters on this figure. We have R vector, which is representing the location of P with respect to the origin. And we have R plus, which is representing the which has the modulus, which is representing the displacement between plus Q and P. And we have R minus, which is representing the distance between minus Q and P. Now the potential at P can be directly found by this equation by substituting the new set parameters upon this equation. The electric potential due to plus Q is, and the electric potential due to minus Q is. As you all see, I added the contributions due to these two charges directly, but the problem within this equation that R plus and R minus necessitates complex vector analysis in order to be defined. So we are going to apply further simplification. Just suppose that in this equation we are given a new angle, which is this angle theta, which is representing the phase of R vector. And as you see, we end up with two triangles. I'm going to apply the cosine rule for triangles upon these two triangles. I'm going to start with the upper triangle, then the lower triangle. Let me now apply this for the lower triangle, but the angle that we have here is pi minus theta, and we know from trigonometry that. Now apply the cosine rule for the lower triangle, and we are going to end up with. This simplification seems good, but it's needed to be simplified more. Now we are going to apply an approximation. Now, according to the fact that the distance, that the length of the dipole, or the distance between these two opposite charges, is significantly small when we compare it to the distance between the origin or the center of the dipole and the point, or by other words, R is significantly larger than D. Okay, and accordingly, this term D over 2 squared is small when we compare it with the other terms, so we can cancel it out from these two equations, and we will end up with let me take R squared as a common factor from these two equations, and we will end up with. We are going to apply the binomial expansion for these two equations. Let me remind you with the formula of the binomial expansion down there. Now let's apply this binomial expansion upon these two equations. Now in this case, x is equal to this term, d over r times cosine theta, and n is equal to 1 over 2. Let me apply this on another paper. Before applying the binomial expansion, we have an error. It needs to be corrected. This power has been eliminated by the square root, so we have only r. Just sorry for this. As we see, the third terms and the other order and the other higher order terms are infinitesimal terms, and they have no tangible effect on the final summation. So we are going to cancel them out. We are going to eliminate these parameters and the other higher order terms, and we are going to end up with a new approximation. Now, as we see, we can directly substitute this into this formula, but it's easier when we substitute it as the reciprocal, or as the reciprocal form of these two equations, because r plus and r minus exist in the denominator. So I'm going to take the reciprocal for both sides for these two equations. Now we are going to apply again the binomial expansion. I'm not going to rewrite the whole terms. I'm going to write the result directly. But what's going to happen is these signs are going to be changed. Now don't be confused. What I did is applying again the binomial expansion that we did before, and I again I took only two parameters because the higher order terms are infinitesimal. Before substituting this, I'm going to take q over 4 pi epsilon as a common factor. Now substitute, and we are going to have, but it's preferred to write the final equation by using the dipole vector. We all know what is the dipole vector. The dipole vector is represented by P, and it's equal to the charge times the distance between these two charges. But as we are handling vectors, this is the displacement. Displacement is not the distance. Now we are going to multiply both sides of these two equations by the radial vector a sub r. I'm going to multiply this by this vector ar, and we are going to see what's going to happen. Now we are going to apply the dot product on this on the right hand side, and we will have, we know how to apply the dot product is equal to the modulus of this vector, which is d, and the modulus of this vector, which by the way is equal to 1. We all know that the modulus of the unit vector is equal to 1 times cosine of the angle between them. And in order to find the angle between these two vectors, let's look at this equation. By the way, the radial vector is aligned with this r vector, okay? This is the radial vector, okay? And d vector, as we see, it's starting at minus q and it's at plus q. So it's so obvious that the angle between AR, the unit vector AR, and d vector is theta. So we are going to multiply by the cosine of the angle between, which is theta, times cosine theta. And as we aforementioned that this equals to 1, so the final answer is As we see, we can substitute the numerator by this P, which is the dipole moment, times the radial vector. Now, and by this we successfully found the potential due to an electric dipole. Now you saw successfully the derivation of the equation for the electric potential due to an electric dipole. Now we will exploit this equation in order to find the electric field due to an electric dipole by only using the gradient operator. We all know that the electric field is the negative gradient, and in order to apply the gradient operation, we will apply the partial derivatives with respect to spatial coordinates for the scalar value. And in our case, we are handling the spherical coordinate system. So we have r, theta, and phi coordinates, which are the radius of the sphere, the polar angle, and the azimuthal angle, respectively. And let's not forget the multiplication of each derivative by the metric coefficient. For example, the metric coefficient for the radius of the sphere is 1. So we are going to multiply by the reciprocal of 1, which is 1. And the metric coefficient for the polar angle is the radius. So we are going to multiply by 1 over r, and so on. Now let's apply gradient operation. Now we are going to substitute the right-hand side of this equation for this formula. Okay, now let me write it. Now, as we see in first term, we are going to take the derivative with respect to r, and as we know, r is the only variable and otherwise are constants. So, and we know that the derivative for 1 over r squared is minus 2 over r cubed. We are going to take the derivative with respect to theta. Cosine theta is the only thing that will interfere with the derivative, and otherwise are constant. And as we know that the derivative for cosine theta is minus sine theta. Now let's assign these new variations in to this equation, and let's rewrite it now. This is the final answer, but in order to reach to a more fancy type of equation, I'm going to take q d over 4 pi epsilon r cubed, these terms as a common factor from both sides. So the final equation is going to be and this is the final equation for the electric field due to an electric dipole. This is the end of our video. See you.